We can start, yeah? Можно начинать. Так. Well, let's start today's lecture. I would like to start today with one very useful proposition, which I have already announced in some weaker form. I have already announced that if we have managed to put two simple closed curves in minimal position, then the resultant picture, the result of these two simple closed curves is unique up to the isotropy of the whole surface. In fact, a stronger assertion is true. So proposition of such kind sometimes are called Alexander method. Why it is method, I explain this somewhat later. It is not very natural to call some statement method, but still. Okay, so we are in the following situations. That suppose we live on a closed surface of genus G, and suppose that we have gamma 1, gamma n are essential simple closed curves. Essential means homotopically non-trivial. It is very long to say every time homotopically non-trivial, so it is convenient to introduce such concept, homotopically non-trivial. Simple closed curves, and suppose that these curves satisfy the following conditions. First, they are pairwise non-isotopic, so these are different up to isotopy curves. Pairwise non-isotopic, and hence non-homotopic, as we have proved that for essential curves homotopy is equivalent to isotopy. Second, that any two pair of them are in minimal position. So these gamma i's are pairwise in minimal position. We do not know what is a minimal position for several curves, but each pair is in minimal position. In minimal position. And third condition, which is this is very natural. These are very natural restrictions, but third one is somewhat less natural. That for distinct ijk, we can consider three pairs: gamma I, gamma j, gamma I, gamma k, and gamma j, gamma k. And at least one of them should be disjoint. So at least one of the sets gamma I cap gamma j, gamma I cap k, and gamma j cap gamma k is empty. So if we draw a graph of intersections, which pairs of gamma i's intersect, then it doesn't contain a triangle. Okay. Well, these are conditions, and now suppose that we have another collection of curves. Now suppose that gamma 1 prime, gamma n prime is another collection of curves satisfying the same conditions. Satisfying the same conditions, and besides, suppose that gamma I prime is homotopic and hence isotopic to gamma I for all I, for each I. Then the assertion is that then there exists an isotopy of the whole surface that takes gamma I, it's better not to draw, that takes, say, gamma I primes to gamma I's simultaneously for all I. So then there exists an isotopy of the whole S that takes gamma I prime to gamma I simultaneously for all I's. Well, this is somewhat long proposition, but still the idea is very easy. That okay, these 1 and 2 are more or less natural, but under this technical condition, if no triple of curves is pairwise intersected, then once we know that each gamma I prime can be taken to the corresponding gamma I by an isotopy, we know that there is an isotopy which takes all these gamma I primes to gamma I's simultaneously. Well, and it is very convenient to have proposition like that. In particular, it follows that if we have only 2 curves, then third condition is always satisfied, and this is always true. So corollary that if we have, before proving, let us formulate 2 corollaries. Corollary 1 is that if we have 2 simple closed curves, alpha and beta, in minimal position, and we have alpha prime, beta prime also in minimal position, and such that alpha prime is isotopic to alpha and beta prime is isotopic to beta. If we have 2 isotopies, one taken alpha prime to beta to alpha and another taken beta prime to beta, then we always have, there exists an isotopy that takes alpha prime to alpha and beta prime to beta simultaneously. And similarly, another important case is when we have 2 multi-curves. If we have alpha n, 1 alpha k pairwise disjoint, so they form a multi-curve, and similarly for beta 1, beta L, then again the graph of intersections is bipartite, and hence it contains no triangles. Again, this condition is satisfied. This is another important situation. Also, if each of the curves can be taken to of course again we have the same collections, similar collections with primes, and if each curve can be taken to this one by a separate isotopy, then there is an isotopy which takes these curves all together. Okay. Before proving this proposition, I would like to show why this 3 is important. It is very easy. Just we can. Oops, sorry. Just we can find some maybe even I do not need genus 2. It is enough to look on the torus. We can consider on the torus, we can consider a parallel, a meridian, and say a curve that goes once around the parallel and once around meridian. So, for instance, we can do it like that. Okay, and in this case, every pair, they are pairwise non-isotopic, they are pairwise in minimal position, but the third condition is not true, since every pair of them intersects, and we can easily make an isotopy of red curve which changes the type of this triangle. And if we replace this red curve with an isotopic curve that passes on other side of this point, then okay, every curve in a new collection is isotopic to the corresponding curve in the old collection, but the total collection, there is no isotopy which takes these curves simultaneously. Okay, now let us prove this proposition.
Если все треугольники, ну, то есть, если условие 3 изменить на то, что все треугольники одинаковые.
It is not so easy to say what does it mean all triangles are. The matter is that we have triangles inside triangles. We have rather difficult pictures when so maybe it is possible to encode some additional information. Yeah, yes, there can be some handles, and so at least it is not easy and it is not obvious. And this condition is easy to check, and it is actually it is very often when it is satisfied. So it's really useful. Maybe it is possible to introduce some very cumbersome data, but it is not easy, and I never see that it is useful. Possible. This is a very bad example. We have also this triangle. This one is also a triangle. So this is a bad example. But at least I'm not sure. Maybe But at least we can add here some handles to destroy all other triangles. So yeah, thank you for the question. Maybe this particular example is not appropriate. Okay, but at least this example shows that this is not good. Actually, we could, instead of curve which passes once along parallel and once along meridian, we could take curve which passes several times, and then this trick doesn't work. So okay, so even in torus it is not true, yeah, without this third condition. Okay, so the proof of this proposition is by induction on the number of curves. So induction on n. The base is trivial since the basis for n equals 0 and we have nothing to prove. Also for n equal 1 the base is also obvious since our conditions that the gamma 1 is isotopic to gamma 1 prime, this is exactly what we need to prove. So n, even n equals 1 is trivial. And now let us make a step. So we assume that we know our assertion for n minus 1 curves, and we prove it for n curves.
Я забыл, у нас изотопия всегда до объемности приближается, да?
Yeah.
Кривая, 10 пересекающих кривых вообще не важно. Какая угодно сложная конструкция, если она изотопия переводится в другую, то и можно на все продолжить. То есть у нас пересечение там, ну, то есть у нас не под многообразие, а что-то более сложное.
Yes, but actually I just this is true what you say, but actually I just claimed that there is an isotopy of the whole S. So our induction how it's called? Induction hypothesis is that there exists an isotopy of the whole S. So okay, we can take first n minus 1 curves and apply the induction hypothesis. And actually we can look on the picture after this. After we so we have an isotopy that takes first n minus 1 curves with primes to the first n minus 1 curves without primes.
А еще у нас кривые телески множественные или, ну мы как бы они поточечно или
Well, yeah, this is a good question. When I say that, yes, curve is a curve without parameterization. So we just, there are two possibilities: either to speak on topological language and just obtain that, just assume that everything, all curves are just sets, or we can speak on and think on smooth language. In fact, they are equivalent in dimension 2. On smooth language, okay, this is just a smooth submanifold, but again as a set. So we may assume that everything here is either topological, or we always have word smooth, but all these things are equivalent to each other. Okay, so we may assume that we have already put the first n minus 1 curves. We have already an isotopy that takes the first n minus curves in the first collection to n minus 1 curves in the second collection, and we may look on the picture after this isotopy, and actually the proof of the induction step descends to the case we just may assume that the first n minus 1 curves are the same. So after isotopy we can look, and we by the induction hypothesis we may assume that just gamma 1 prime equals gamma 1, etc. Gamma n minus 1 prime equals gamma n prime, just as sets. And n minus 1, sorry. And the only pair of curves which are not equal to each other is gamma n prime and gamma n. So let us consider the union of this n minus 1 curve. Let's denote by gamma capital is just the union of the first n minus 1 curves. I will say that this is a graph on S. This is not so good. This is not a graph in usual sense. The matter is that, okay, graph consists of vertices and edges, yes? And this gamma, maybe there is some gamma I which is separate from all others, disjoint from all others. Then this gamma I is just a circle without any vertices. Okay, just for today, I allow a graph to contain such circles. It is not convenient to introduce vertices, and there is no need to do it. So just when I say graph, I mean that it is usual graph, maybe plus several circles without vertices. Okay, so we have this graph, and we have curves gamma n and gamma n prime. And my goal is to construct an isotopy of S that fixes gamma. Fixes gamma in the following. I mean that it fixes its setwise, so it fixes it as a set, but also it fixes every component. So it fixes every vertex of graph and every edge. So goal is to construct isotopy of S such that this isotopy fixes every vertex and every edge of gamma. And every edge of gamma. And takes gamma n prime to gamma n. If this is done, then we get the required isotopy. Just note that I do not want to fix gamma pointwise. There is no need to fix gamma pointwise, and it would not be true if I try to fix gamma pointwise. The matter is that suppose we have an edge of gamma, and gamma n intersects it like that, and gamma n prime intersects it in another point. It is not possible to fix it setwise and to take gamma n to gamma n prime, but it is possible to, I will prove that it is possible to fix it, every edge, every vertex and every edge of gamma. Okay. First easy observation is that neither gamma n nor gamma n prime passes through vertices of gamma. Why? Because every vertex of gamma is intersection of two of these n-1 curves. So if gamma n passes through this vertex, then we have a triple with all three intersections non-empty. So the same for gamma n prime.
Неправда. Потому что гамма n штрих минимальный позиции Z. Или минимальный?
В минимальном. Gamma n primes satisfy all the same. I have made some shift of notation. I said that I have already performed an isotopy for the first n-1 curves, and the general case was reduced to the case when the first n-1 curves coincide. Then this is okay. Okay.
Yeah, but the isotopy was also applied to gamma n prime.
Yes.
Yeah, but this condition doesn't change under the isotopy.
Yes. Yeah, these conditions doesn't change under isotopy, so it's okay. Okay, and since this is true, then well, for each edge of gamma, we have the following picture. It is intersected by gamma n maybe several times, and it is intersected by gamma n primes. Maybe some of the intersection points coincide. So we have no reason why gamma n prime and gamma are in some general position. We know that gamma is in general position with respect to since they're in minimal position. In particular, we know that all intersections are transversal. So we know that gamma is in general position with respect to gamma n is in general position with respect to gamma capital, and gamma n prime is in general position with respect to gamma n capital, but we do not know anything about the total three. So it is possible that we have such situations, but it is easy to make an isotopy of. So the first step one, is we would like to make an isotopy of the whole surface that fixes gamma. When I say fixes gamma, I always mean fixes in this sense. That fixes gamma and makes gamma n prime. So I apply this isotopy only to gamma n prime, and not to gamma n, and makes gamma n prime in general position with respect to gamma n and gamma capital. In general, not in minimal position, just in general position, so that it is transversal and we have no triple intersections and so on. In general positions with respect to gamma n cap gamma capital. Why it is possible? Okay. First of all, it is possible near this edge we just may make some, if we have such triple intersections, we just have some isotopy which takes red curves somewhat closer to one of the ends, and to destroy this triple. And then outside we just put it in general position. Do not perturb in gamma at all. So okay, this step is more or less obvious, and now we may assume that all these curves are in general position. Step 2, that I would like to put gamma n and gamma prime again. By step 2, we would like to make an isotopy of S that fixes gamma and makes gamma n prime in minimal position with respect to gamma n. An isotopy of S that fixes gamma. Yeah, one important thing, I would like to be more precise here. I would like that all these isotopies fix gamma through the isotopy. So they fix, when I say that it takes gamma n prime to gamma n or to some, I just say about the beginning and the end. But gamma should be fixed through the whole isotopy. Through the whole isotopy. Okay, and now I would like to make gamma n prime in minimal position with respect to gamma n. I don't want to write it, but I still want after this step, I still want gamma n prime to be in general position with respect to gamma. So we would like to put it in minimal position with respect to. Okay, how to do this? Yes, and note that before saying how to do this, let us note that gamma n prime is isotopic to gamma n by our conditions. So when it is in minimal position, it is just disjoint from gamma n prime. So we just achieve that gamma n prime is disjoint from gamma n. They are isotopic, hence the minimal position is when they do not have crossings at all. Okay, and here we apply a Beigen criterion. So suppose gamma n prime and gamma n are not in minimal position. Then they form at least one Beigen, and moreover they form at least one empty Beigen. So if gamma n and gamma n prime are not in minimal position, then they form an empty Beigen. So we have a picture like that. This one is gamma n, this one is gamma n prime, and a region between them is these two arcs. Since it is an empty Beigen, this arc doesn't intersect gamma n, that arc doesn't intersect gamma n prime, vice versa. So we have no other intersection points of gamma n and gamma n prime on this Beigen, and this region is homeomorphic to a disk. Now let us look how this Beigen can intersect with the graph gamma capital. Note that, well, I claim that the intersection is just like that. We have several disjoint arcs, edges of gamma. We have no vertices inside, and all edges go from this arc to that arc and do not intersect with each other. Why this is so? Okay, look on all gamma i's with numbers with indices smaller than n, gamma 1, gamma n, 1 and so on. Some of them may intersect gamma n, and some of them do not intersect. Note that okay, this is what I want, but what can happen here? Assume that we have at least one vertex of the graph gamma inside the bigon. So if there is a vertex here, then this is some gamma I and this is some gamma j. Look on the curve gamma j. Gamma j is essential curve. It is homotopically non-trivial. Hence, it cannot be contained in this disk. If it is in the disk, then it is homotopically trivial. So gamma j must go outside this bigon. So gamma j must intersect at least one of the curves gamma n and gamma n prime. Similarly, but okay, hence gamma j must intersect both of them. Why? Because gamma i's are in minimal position and gamma I primes are in minimal position. Hence, the number of for each I, the number of intersection of gamma I with gamma n equals to the number of intersections of gamma I with gamma n prime. So if at least one of them is non-zero, then both of them are non-zero. Hence, we see that gamma I intersects gamma n, and similarly gamma j intersects gamma n. We have contradiction with this condition 3. So this is impossible. Hence, we have no vertices here. And how can... So only edges of gamma may intersect this bigon. How can an edge of gamma intersect a bigon? There are only two possibilities. It may intersect twice the same arc, or it may intersect like that. I mean that I just would like to consider one arc of an edge inside the bigon. It may go either in this way, or in this way, or in that way. Only 3 possibilities. But these are not possible, since in these 2 possibilities we have bigons between one of the curves with smaller numbers and either gamma n or gamma n prime.
So not a minimal position.
Yeah, and so we have not a minimal position either for one collection or for another. So these are impossible, and the only thing which is possible that we intersect several edges of gamma in this way. Okay, if the picture is like that, then it is not hard to make an isotopy of gamma n prime, which preserves all these edges. We just move. Well, yeah, and they are not. If they intersect, then we have a vertex inside. We have already discussed this. So no intersection. So we just move this gamma n prime along these curves and make an isotopy which replaces gamma n prime by the curve like that. So we have decreased the number of the intersection points of gamma n prime and gamma n, and then we repeat the same procedure until we have gamma n and gamma n prime are not in minimal position. We have a beigen and we can apply such procedure. So this finishes step 2. So we achieve that gamma n and gamma n prime are
in minimal position.
Hence are disjoint. Now look on the on how gamma n and gamma n prime decompose the surface. We have already discussed this. That okay, first of all, gamma n is homologous to gamma n prime. Hence, together they decompose a surface into two parts. So the only possibility is that gamma n and gamma n prime bound an annulus, a cylinder. If this is not so, then we have discussed that in all other cases, if both parts are of positive genus, they are not isotopic to each other. We started from this on the first lecture. So only such possibility, this possibility, or maybe gamma n and gamma n prime are separated, but still they must bound an annulus. So we see that gamma n and gamma n prime bound an annulus. And now let us look on this region between them, on this annulus. So we see that gamma n and gamma n prime bound an annulus. So we have, this is gamma n, this one is gamma n prime, and again look on how this annulus intersects, how this annulus intersects with the graph gamma capital. Look, is it possible that we have a vertex here? If we have a vertex here, then again, if we have some gamma I and gamma j, if both gamma I and gamma j intersect the bound either gamma n or gamma n prime, then we come to a contradiction as in the previous case. So the only possibility is that one of the curves gamma I and gamma j is disjoint from, is completely contained in this annulus. If both intersect the boundary of the annulus, we come to a contradiction with this condition. So one of gamma I and gamma j, without loss of generality, this is gamma I, is contained in the annulus. Now it is not true that any curve in the annulus is not a disk, so it is not true that any curve in the annulus is homotopically trivial. But up to isotopy in the annulus we have only one homotopically non-trivial curve, this one, and it is isotopic to the boundary. But now we still have not used the first condition that curves are pairwise non-isotopic. Now it is important that this is also not possible since gamma i's are pairwise non-isotopic. Hence, we have no vertices inside. And again, we have the same picture. Also, we cannot have bigons like that again because of the minimal position. So the only possibility for intersections of the graph gamma capital with this annulus is that we have several intersections with edges like that. And again the same situation. Now we can consider an isotopy that fixes edges of gamma, so we may move gamma n prime along these edges to gamma n. So there is an isotopy which takes gamma n prime to gamma n and fixes the graph gamma through the isotopy. If it comes several times around, then it is not simple. Yes, there is only one simple curve. Of course, there are curves which are non-simple, but we always speak about simple closed curve. Okay, this is the proof, and now. Two remarks. First, okay, we have finished the proof, but now actually this proposition has a generalization. I didn't want to start with this generalization since it is already rather long formulation, but actually we can consider a surface with several punctures and boundary components. In fact, just for a moment, when we speak about surface with punctures, then there are two equivalent languages. We may say that these are indeed true punctures, that we delete this point from our surface. So we consider surface without this point. Or we can just may consider a compact surface and mark some points. So we can consider surface with punctures, or we can consider surface with marked points. Of course, these are different objects. One of them is compact, another is not, but they are completely equivalent to each other in all situations. And sometimes it is convenient to work with one of them and sometimes with another of them. When we speak about hyperbolic metrics, it is convenient to have punctures, since we have no metrics at all in these punctures and we go to infinity when we approach it. But at the moment it is more convenient to me to speak about marked points. We may pass from one language to another as it is convenient to us. And if we speak about marked points, we can speak on arcs which connect these marked points to each other. It is not so convenient to speak about such arcs when we deal with punctures. So in this situation, the same proposition is also true, and moreover, we can consider these gamma 1, gamma n may be either simple closed curves. Each of them is either simple closed curves or an arc. An arc with endpoints of the arc may be either on the boundary components or in marked points. With endpoints in marked points or on the boundary components. And the same is true, and all isotopies we may assume that they fix the boundary pointwise. And then all the same is true, and the proof is the same with very slight modifications. So the same works in this situation as well. This is first remark. And what I would like to well, and we have another useful corollary of this proposition. The proposition itself is purely topological. We have no hyperbolic matrix or something like that in this proposition. But now suppose that we have a hyperbolic metric, and suppose that we have only one collection of curves which satisfies these conditions. So corollary that suppose that SG is endowed with a hyperbolic metric, and suppose that gamma 1, gamma n is a collection of simple closed curves satisfying these conditions 1 through 3. Then there is an isotopy which makes all these curves geodesics simultaneously. The matter is that geodesics are in minimal position. This is an immediate consequence, but this corollary is often useful.
And why do we have the third condition for geodesics?
No, since it is since we have it for gamma n's. The third condition for gamma I primes follows from the third condition. Both of them are in minimal position. Well, hence gamma n 1, gamma n can be made geodesics by an isotopy simultaneously. And there is another useful corollary. Which maybe is not so obvious from the very beginning. Suppose that we have two simple closed curves, alpha and beta, are simple closed curves in minimal position. And suppose that we have another curve gamma. Gamma is also a simple closed curve. Then there is a simple closed curve which is isotopic to gamma and is in minimal position both with alpha and with beta. Then there exists a curve gamma prime such that gamma prime is isotopic to gamma and is in minimal position with both alpha and beta. I would like to say that it is not so obvious. It may seem to be obvious, but yeah, the proof is like that we have an isotopy which makes this alpha and beta geodesics. if alpha and beta are geodesics, the corollary is obvious, since we just take for gamma prime the geodesic representative of the isotopy class of gamma. And now this corollary allows us to reduce the general case to the case of geodesic alpha and beta, since they can be made geodesic. But okay, this corollary can be proved without any hyperbolic geometry, purely topological. But it would be it would require some.
Don't we need this third condition here?
No, I don't want to apply this proposition to 3 curves here. I want to apply it just to alpha and beta.
Okay, we apply them to alpha and beta and we get geodesics.
Yeah, alpha and beta can be made geodesic.
Okay.
But now there is a curve. Now we know that every isotopy class contains a geodesic representative. We just take this geodesic representative and it in the isotopy class of gamma, and it is in a minimal position with alpha, and it is in a minimal position with beta. So in this corollary, I don't want to apply this proposition for the 3 curves, since it is impossible. They do not satisfy. Well, and what is with well, and well, now why this is Alexander's method, and what is this method for? Actually, now it's time to turn to the mapping class group, since it is the title of the course, but for a long time I have spoken nothing about mapping class groups. Now let us start to deal with mapping class groups. Actually, this is a method for proving that some mapping class is trivial. So suppose that we have an element. Again, there is a version of this for surface with marked points and boundary components, but I would prefer to speak on closed surface. It is easier to understand what is the analog. Suppose that we have a mapping class, and okay, sometimes we can prove things like that. That for, say, this mapping class takes some curve, some particular curve, to a curve isotopic to it. At least things like that sometimes can be proved by hands. So it is possible just to check. This is condition which is possible to check if it is satisfied. So we may assume that we have several curves. This is an often situation that we have simple closed curves, and we know that okay, here actually when people deal with such situations, mapping class cannot be applied to a curve. It can be applied to an isotopic class of a curve. But I would say that phi takes, let it be f, I'm sorry, f takes every gamma I to a curve isotopic to gamma I. it is better to say that f. It is better to say that f takes to itself.
We suppose that it does that.
Yeah. The isotopy class of gamma I. So it is better to formulate it in this way. We suppose that this is true, and I just want to say that this is a kind of conditions which usually can be checked if they are true. Okay. Now, what can we say? And since we are speaking of isotopy classes, we can always choose representatives that are in minimal positions. So we can always assume that these two conditions are satisfied. Assume that the third is also satisfied. This is an assumption. So assume that we have found several curves. Each of them, the isotopy class of each of them is fixed by f, and these curves satisfy our conditions. So this is an assumption. So in fact, an assumption is only condition 3. We can always make conditions 1 or 2 to be satisfied. So if this is true, then what can we say about this f? First of all, we can always say that f can be so I would like to find a good homeomorphism inside this mapping class f. So I say that there exists a homeomorphism phi in mapping class f such that phi takes to itself the graph gamma, where now gamma is just the union of all curves. So if we know that the mapping class stabilizes every isotopy class, then we can represent this mapping class by a homeomorphism so that it preserves the graph gamma. Why this is true? Okay, we first can consider an arbitrary homeomorphism in the mapping class, and then this arbitrary homeomorphism takes curves gamma 1, gamma n, let it be psi. It takes them to some curves gamma 1 prime, gamma n prime, and what we know? We know that these curves satisfy all that conditions. Curves gamma 1 prime, gamma n prime satisfy all that conditions, the same conditions, and since f takes to itself the isotopy class of gamma I, we know that gamma I is isotopic to gamma I prime for each I. So we are completely in the situation of that proposition we have proved. And now what we know, that there is an isotopy of the total surface that takes gamma 1, gamma n to gamma 1 prime, gamma n prime. Changing our psi by this isotopy, we achieve that the graph is stabilized. I'm sorry, but now note that it is stabilized not in that sense which I talked before. them well. Consider an example like that. Consider just maybe, do I have an example on the, well, I have an example on the torus, yes. I consider one curve like that. This is gamma 1. And another curve this one is gamma 2. Yes? And phi, which I consider, would be rotation around this axis, rotation by pi. Half rotation. So it takes gamma 1 to gamma 1, gamma 2 to gamma 2, but it doesn't stabilize every edge of gamma. It takes this edge to that edge, and vice versa. So sometimes it happens that it is like that, yes? But still we know that the graph is stabilized by here as a set. No, not every edge is stabilized. Okay, but now, why this is useful? Okay, at the moment it is not completely clear why it is useful. It is useful it is especially useful if we add some additional condition. One says that a collection of curves which satisfy these conditions, which are in minimal position, pairwise and isotopic, and so on, this collection of curves fills the surface if we can remove all these curves, their union from the surface, if we obtain the only disks, if all connected components of the complement are disks, if all connected components of S without are disks. Yes, n is greater than 1. Soon we will see that there are two simple closed curves which fill every surface can be filled by two simple closed curves in minimal position. Actually, look, this is first of all, we need that gamma is connected. If gamma is disconnected, then this cannot be true. And if gamma is connected, then we need that our curves destroy all handles. More intuitively, this means that this union goes through all handles, that it destroys all handles. So the idea is that if the curves intersect many times, then usually, if they intersect in some complicated way, then usually they fill. So it is a thing which can be achieved by choosing curves.
Yeah, it makes gamma the one skeleton of CW structure on the surface.
Yeah, but okay, it is not so hard to introduce a CW structure on the surface, so it is not so useful that this is a CW structure. But what is useful? A useful thing here is that, well, for a disk we know that any homeomorphism of a disk. One remark, one important remark, that if we speak not about closed surface, but of a closed surface with marked points and connected components, then here are either empty disks without marked points or disks with a single marked points. If there are two marked points, this is not good. So a correct generalization is like that. Okay, and look, if we have a homeomorphism of a disk to itself, which fixes its boundary pointwise, then this homeomorphism is always isotopic to the identity modular relative to the boundary. Hence, suppose that, okay, we know that this phi stabilizes gamma as a set, and suppose also add to all these assumptions, add the assumption that gamma 1, gamma n fill our surface. Then we have here some automorphism of a graph. If this automorphism, just combinatorial automorphism of a graph, some vertices go to vertices and edges go to edges. If this automorphism is combinatorially trivial, then we can always isotope. By an isotopy, we may achieve that phi stabilizes gamma pointwise. If it stabilizes two vertices and takes this edge to this edge, then we can always change slightly this homeomorphism so that it stabilizes this edge pointwise. But now gamma is a finite graph. It is a graph with finitely many vertices and finitely many edges. So we may consider, okay, any phi of this kind induces an automorphism of gamma. Let it be phi with phi star. It is an automorphism of gamma. And any automorphism of a finite graph is always an element of a finite order. Hence, we may say that there exists k, such that if we take phi k star, this is a trivial automorphism of gamma. Trivial automorphism of gamma. Then for this, we may assume we may replace phi to the power k, we may replace by an isotopic homeomorphism psi, so that this psi stabilizes gamma setwise or pointwise, any point of gamma. And now, if this graph gamma fills the surface, then we see that we have only all connected components are disks, and the boundary of each of them is stabilized pointwise. So we may, by a further isotopy, we may achieve that psi is just the identity automorphism. Well, up to isotopy. What we see? We see a wonderful corollary. Suppose that we have a mapping class group, a mapping class, and we have curves gamma 1, gamma n that satisfy conditions 1, 3, and also fill the surface. And suppose that f takes to itself the isotopy class of each of these gamma i's. Then the claim is that under these conditions, f is of finite order. And moreover, if we see that this automorphism of a graph is trivial, if in addition this automorphism is trivial, then f just is a trivial mapping class. So this is a method for proving that some mapping class is trivial, or at least is of finite order. And this is very useful method since this condition is something that we can check. Well, we need to make a break. Just one word. That for instance, we will deal with several relations in mapping class groups. We may start considering den twists and study relations between them. There are plenty of such relations. How to prove some relation? For instance, we intuitively we understand that there is a relation of the following kind. How to prove that some mapping class is trivial? The usual method is to find good collection of curves. For curves, we can just draw how this mapping class acts on curves. This may be cumbersome, this may be difficult. We may do it by computer sometimes, but it is possible to look how our mapping class acts on certain curves, and then we can apply this usual procedure. Okay, let us do a break, 10 minutes break. Then resume. Well, next thing which I suggest to discuss, and I hope that maybe this is better to discuss this thing in some, and not in the regime of a lecture, but in some. I hope we shall discuss them together. We can look on den twists. I recall that den twist is a transformation, a mapping class which is defined like that. We consider a simple closed curve. We cut a surface along this curve. Then if we have some test curve, this test curve, then we rotate one of the boundary components by the whole rotation by 2 pi. So the test curve becomes to be like that. There is, I can't say it in English, but как у Свифта остроконечники, тупоконечники, также тут есть те, кто использует правые твисты Дэна, и те, кто использует левые твисты Дэна. Вот. So left and right den twists are used sometimes left, sometimes right. I prefer to use left den twists.
Left den twisters and right den twisters.
Yes, when we approach this curve, we go left, as it is written here, and then we glue it back, so that the test curve behaves like that. Note that the den twist is independent on the orientation of this curve alpha. If we approach from here, then we turn left, and we approach from here, we also turn left. So the den twist is given by a non-oriented simple closed curve. There are left and right den twist about this non-oriented simple closed curve, but the orientation of this curve is irrelevant. So the den twist will be denoted by T alpha. Of course, as a homeomorphism, it is not well defined, since we have many possibilities to realize it as a honest homeomorphism. But as a mapping class, this is well defined, and it depends only on the isotopy class of alpha. And of course, if alpha is a homotopically trivial curve, then this is just identity, so it is not interesting. Well, and there is a very useful technical proposition which relates den twists and geometric intersection numbers. Namely, suppose that we have the following situation. Suppose that alpha 1, alpha n is a multi-curve. So this is a collection of pairwise non-intersecting. I always, I don't want to repeat it many times, but all curves are essential, and I always mean that these curves are pairwise non-isotopic. So just multi-curve, which means that these curves are disjoint. Then, of course, for disjoint curves, den twists about them. At this moment, maybe this is the last moment when I try to distinguish between curves and their isotopy classes, so that A1, AN be isotopy classes of these curves. Of course, the corresponding den twists commute, pairwise commute. when two curves are disjoint, of course, mapping classes commute. And it is natural to consider mapping classes like that. We can consider a mapping class which is some multi-twist, which is product of some powers of this then twist. Okay, this is, once we have a multi-curve, we have infinitely many then twists, infinitely many mapping classes of such kind. And we may act by this particular mapping class on some other simple closed curve. So let us consider B isotopy class of simple closed curves. And there is the following technical proposition, but very useful. We may look on geometric intersection number of the following thing. We may consider f of b with b. And it turns out that there is a completely explicit formula for this. And I suggest we try to find this formula. But the formula, an explicit formula exists only under some additional assumption. Additional assumption is that our powers are positive. Actually, of course, the geometric intersection numbers doesn't distinguish between left and right. Hence, the same formula will be true if all of them are negative. But an important condition, which is really important, is that they have the same sign. So either all twists are positive or all twists are negative. Okay, and okay, I may write down the answer, but maybe it is better to consider it as a problem which we want to solve. Yeah, we may start from case n equals 1. So in case n equals 1, we just are interested in this particular. Oh, no, not in this. In that one. For k equals 1, it's also interesting. So we may start even with n equals 1 and k equals 1.
Ну, сейчас для А это точно К.
Может быть, надо прибавить количество пересечений между B и A плюс K.
Okay, I suggest we try to count it, not to try to.
Но мы же можем в маленькой окрестности вот этот твист сделать. Соответственно,
Yes.
то, что все пересечения, которые в маленькой окрестности, они с ним ничего не делается. Если посмотреть, что было. Если К равно 1, то это просто количество.
Сейчас нужна идея про то, что это и от АБ
Нет.
плюс К не нравится.
В квадрате. Ну, Ну, у нас есть, вы пустите по карну 1, да? Получится количество точек пересечения в квадрате, правильно?
Ну, там вообще может быть добавиться, если у нас обратных не ставят.
Ну, мы в каждом пересечении мы наматываемся, проходим по каждому. Потом во втором, потом опять по каждому, третий опять по каждому. Получается в квадрате, да?
Число. Что значит в каждом пересечении? Там, ну, А, она...
Пересекается вот раз. Да. Мы доходим до первого пересечения, проходим по всем, возвращаемся обратно. Идем до второго, проходим опять по всем, возвращаемся обратно. Получается в квадрате.
Сейчас, вообще перестал понимать, почему количество пересечений.
Здесь два раза пересекалось. Сколько будет?
Сейчас B это произвольная, да?
Да.
Наверное, 4.
Где зависимости от Б.
Не, петлями два раза пересекаем.
Да, в квадрате.
Будет 4 пересечения, наверное.
So,
Можно...
Ну, К умножить на количество пересечений раз Б, вот все.
Что?
К умножить на количество пересечений.
Почему умножить?
Ну, потому что почему ты говоришь, потому что каждый оборот он проходит по всем.
какая формула?
Я думаю, что умножить. Конечно, и от АБ умножить на К. Ну, потому что в квадрате...
Пусть карна 1.
Ну, тогда должно быть просто и от АБ.
Пусть они пересекаются два раза. Да?
А, ладно, да.
Мне не нравится.
Да, ладно, согласна.
Мне кажется, тебе надо в квадрат завести.
Нет, ну,
Да,
Ну, если-
правильно.
а вот как надо завести квадрат, я не знаю.
чем на торе посмотреть можно на параллели меридиан, например.
Про меридиан интересно, один раз пересекаться, там будет тоже 1.
Ну да,
Ладно, состояние. Почему один?
один. Ну ты в одном.
Да,
крутил,
да, и К на И в квадрате
сколько
какая.
раз.
Вот это вот это.
А, вот это
В
параллель.
квадрате на К, да?
Да,
Yeah.
На много К.
ну да.
Okay. This is the correct formula, but let us try to prove it. Okay.
Ты сказал, что не зависит от натории, что не зависит для меридиана параллели не зависит от К.
Потому что медиан направление интересно рассматривать, потому что у них одна точка пересечения, мы не различим квадрат числа И, а просто числа. Да.
We may look. We may consider this B and look on all intersections with A. So this is A. Actually, we can consider small neighborhood of A. This is just a rectangle. For convenience, let us introduce some particular coordinates in this rectangle. So this neighborhood is just 0, 1, which is the coordinates along alpha, times some 0, epsilon, which is a coordinate in direction orthogonal to alpha. And let us do in the following way. Let us proceed in the following way. It is convenient to let us orient this B. It is not good to say B, it is better to say beta, which is a curve in isotopy class B. But now the second curve will go, for instance, on the right from B, from beta. It goes on the right from beta on some particular small distance. Yes. Then it arrives here and it starts to go linearly. Just linearly, so that it makes k turns when it passes here. Okay? And then we proceed. And so on. But when we arrive here, then we again go left and choose our direction so that we make k turns when
K rotations, yes?
k rotations before we pass to there, and so on. This is beta prime. Let us compute the number of crossings of beta prime with beta. Here, okay, we have this arc from here to here. This arc crosses, it goes k times along this red strip. Hence, it crosses each of these segments k times. So the number of crossings is k times yeah, of course, alpha and beta are initially in minimal position, of course. So we have k times, but this is the number of crossings for one arc. Yes? I just consider this arc which starts here and arrives here. The number of crossings with beta is like that, but there are as many such arcs as the number of intersections of A and B, so we get this one. Yes? Assume that k is positive, of course the k is negative.
Можно еще раз? Я не понял, почему Кана... Сейчас вы говорите, что в треугольнике пересечению беты...
Не, я беру, вот я сюда пришел и пошел налево, да, пока не дойду вот до сюда. Да. И смотрю вот эту дугу, вот отсюда вот до сюда.
Да.
Она k раз проходит вдоль полосы. Поэтому она каждый из вот этих вот отрезочков пересекает k раз.
Да.
Общее количество пересечений k на I от AB.
Не k раз, а I от AB раз.
Нет, каждый из них пересекает k раз. А этих отрезочков I от AB.
Ну, хорошо, да, но откуда еще это на I от AB?
Ну так теперь я должен рассмотреть такую вот эту дугу, вот эту дугу и так далее.
Ну, то есть просто когда мы, тут картинка такая, что мы когда рассматриваем эту дугу, мы на самом деле по другим тоже проходим.
Да, когда мы идем вот отсюда налево, мы проходим по всем ним, по каждой по k раз.
То есть мы проходим из-за того, что мы по А идем, а потом мы проходим потому, что мы по В идем.
Но теперь рассмотрим вторую дугу, которая отсюда сюда ведет. У меня кривая бета-штрих.
Так, мы идем по бета и
состоит из вот таких дуг, которые бета вообще не пересекают. И из вот таких дуг,
да,
которых I от AB штук.
Давайте, я согласен, их I от AB штук.
Теперь посмотрим на одну из этих дуг.
Да.
И посчитаем, сколько раз она пересекает бетту.
Хорошо, да, но вот я не понимаю, видимо, почему она пересекает ее k.
Эта дуга проходит k раз по всей длине, это все одна полоска. Ну, у меня одна кривая альфа.
Одна кривая?
Это все одна кривая. Вот это. Это просто разные места одной и той же кривой.
Да.
Когда я делаю каждый оборот, я прохожу по каждой из этих по одному разу. И получаю I от AB. Но когда я делаю k оборот, я получаю k на I от AB. Ну, соответственно, всего количества.
Да.
Okay, we understand that for these particular two curves, the number of crossings is k times I of AB squared. A natural question is why these curves are in minimal position.
Orientation is the same of the beta cross.
Well,
The orientation is the same of the crosses, so the algebraic intersection
no, not so. The matter is that it is not, if we orient alpha, then it is not true that all these orientations are maybe any. They are not all of the same sign. If we start moving here, we move in positive direction. So when we arrive, when this arc arrives here, it moves it moves from here. And this one is of different sign. So it is not true that all crossings are of the same sign. It would be too good. Yes, we need to prove that there are no bigons in this particular situation. And moreover, it is sufficient to prove that there are no empty bigons. Well, yeah, for a moment, before proving this, how do you think, what is the answer here?
Сумма таких. Ну, в смысле? Сумма проекта.
It's the sum of kj. We can this one by e of ajb squared.
Будет, конечно, сложнее.
Yes.
Байгона нет.
We may we may construct beta prime completely in the same way, and the number of crossings will be the same. Yes. So this computation that the number of crossings is this. It works as well if there are several alphas. Yes.
Ну, надо понять, что байгонов нет между.
Yes, but note why this condition is important. Only if this condition is satisfied, only under this condition there are no bigons. Actually, if there are several curves alphas, then bigons may exist, but only if two k's have different signs. Sorry. Well, but let us try. Okay, every bigon. If assume that a bigon exists, this bigon is formed by an arc of beta and an arc of beta prime. Yes. Which arcs of beta do we see here? Let us start with beta. Beta is easier. There are short arcs of beta, and there are long arcs of beta. Let us start with short. It is easier for understand. Short are I mean that an arc is short if it is inside the strip. So if it is some arc between two consecutive let us I would like to have wide strip to be easier to draw, and suppose that these are two consecutive arcs, and this is an arc of beta, short arc of beta. Look, these two consecutive arcs, there are two possibilities. There is a possibility that this arc is the first, I mean that it goes let us consider another possibility, that this one is not the first. The first is which goes from here. Then these two go as well until we come to some other.
Со стороны действительно выглядело, как будто
Очень громкая дверь.
хотел уйти, громко хлопнуть дверь.
Well, we move until we meet beta another time. Yes?
Если пересечение больше одного, то вообще там внутри еще...
Если это не первое пересечение, не крайнее. Да?
Что там крайне получается?
Там как бы в этом прямоугольнике есть вход и выход.
У нас нет крайнего пересечения, мы сразу уходим, там нет пересечения.
Нет, у нас вот здесь вот есть много разных пересечений, да? Вот, допустим, это не первое, да?
Тогда он не пустой, если...
Тогда мы идем и втыкаемся в эту бета еще раз.
Если больше одного индекса.
Да не важно. Ну, в ту же самую или не в ту же самую. Главное, что мы втыкаемся в бет. Кстати, здесь есть одна... we need to be careful. Here, one of them may appear to be the first one. So maybe only one of them goes to beta. Yes? Mm-hmm. But in any way, this is not a beigen. A beigen can be only if this one is continuation of that one. And it is completely impossible. Or yes, it's easier. They go one direction. They go one direction. They cannot be intersection or continuations of each other. Yes. Yes. In all cases, it is easy. So there are no beigens with small arcs of beta. So we need only to consider large, long arcs of beta. And so this is always the question of we need to consider here the first and the last. And let us draw it in more details. So,
вот мы поняли, что там нет бегонов, просто, ну, то есть это же можно график вот этой кривой прямоугольника.
Да. Все просто. Да. Они просто идут в одну сторону, они не могут быть одно продолжением другой. А теперь давайте нарисуем, давайте посмотрим на длинную эту самую, да? Я просто не хочу стирать этот рисунок. Давайте нарисуем здесь. This is beta. And we have two consecutive crossings with alpha. And here we have two cases. It is possible that these two intersections are of the same sign or of different signs. Okay. Here we have these strips, and we have the following situation. This is arc, which is the last one, so it goes here, and here it becomes the first one. So this is our long arc, but now we arrive to the next arc, which crosses beta here.
Это один из двух случаев, когда альфа.
At the moment, it is not important. It is not important. I'm sorry. Well, we may ask whether this one is a beigen or this one is a beigen. So we have two possibilities. But concerning this one, again the same situation. These two curves travel in the same strip in the same direction. and they cannot be continuations of each other. Yes? So the only interesting question for us is whether is it possible that the beigen is here, on that side of. So we study this long arc of beta, and we are interested if it is possible that a beigen is on that side of.
Вот кто 50 там, а ушла вниз, это был бы другой случай же.
No. We always go left. All these are of the same sign. So independently of all orientations, we always have positive signs here. We always have left then twist. So all these коэффициенты наклона всегда положительные. Okay, we are interested in this beigen. And now, I was not correct. It is not interesting for us at all, the orientations of these two green. An interesting thing is the orientations of these. We have here orientation of beta, we have the induced orientation of beta prime. This one is always oriented in that direction. But concerning this one, there are two possibilities. It can be oriented either here or there, or both are. But look, if this orientation is, if it is oriented in this way, then your arguments work. These two crossings have the same sign, and so this is not a beigen. We need not think of how this curve travel and so on. If this, sorry. And now assume that this one is oriented like here. Yes. If this is the same, then this one travels along this strip, and this one goes here. It must go inside this strip, and hence we would have a beigen between alpha and beta. Okay.
Если мы пошли направо, ну если вовлекая разных знаков, то сломаем, да,
yeah. If the signs so we have proved that our curves are in minimal position. Hence we have proved this proposition, in particular for one curve, but the same works for several curves. So, but if ki's were of different signs, then it would be possible that the following situation holds. That here, one moment. Say this one is negative, so here we go to the right. Yes? And here this one is positive, so here we also go to the well, this is a beigen.
Зачем мы туда вообще сходили сейчас? Потому что мы так считаем, да?
To compute the number, we need to introduce to agree. We may travel on the right of our curve or on the left, but we need to agree. If we agree to travel on the right and compute the number, but here is a beigen, so it is not true. Yes, the correct formula, but it is a result by Nikolai Ivanov, as far as I know, somewhat about 1980s. Here, in general situation, there is the following estimate that this one is less than or equal to this value and greater than or equal to so in general situation there is only such estimate. We cannot say more or less only 2 points can be deleted in this way for each.
Можем брать двуугольник, если у нас идем там направо.
Yes. Yes.
Две точки. У нас вообще сейчас все двуугольники.
Это какая-то немножко странная оценка, если там, например, просто знак, ну, если это там, если
Yeah, this estimate is useful only for large case. It is not interesting if this case are ones or minus ones. So the situation of different signs is more difficult, and actually this is some you may consider as an exercise, but this is exercise which is not easy.
Вот если мы пройдем по бета и посчитаем количество перемен знака, и выщем 2 умножить на количество перемен знака, не потому что мы получим правильный ответ.
Я не уверен, что мы
правильно. Что не будет других двуугольников, мы взять, которые...
Я не очень уверен.
Мы можем...
Да, там...
Ты можешь стянуть один, потом появится другой.
Там что-то может итерироваться, там, ну, вот такая оценка есть, но, ну, в общем, это более сложное.
А можно, вот если, вот если, например, там их просто, ну, вот у меня две, ну, есть А1 и А2, и знаки плюс-минус 1, то тоже ничего не понятно?
По-моему, тоже не. Ну, можно думать, там в каких-то случаях все. Надо, каждый раз надо рисовать. Я вот наизусть вам ничего не скажу. Вот. В каких случаях что-то можно сказать, но такой вот общей формулы нету. То есть общая формула вот только в этой ситуации. Окей.
Когда мы доказывали, тут нельзя подключить аргумент про ориентацию, что нашу бизнес-ориентацию, умножать ориентацию на какой-то гомоморфизм путей в плюс-минус 1. Хорошо,
Я думаю, можно.
И что вы хотите доказывать?
Ну, я хочу сказать, что мы будем рассматривать не просто ориентацию на этой картинке, а ориентацию буду умножать на гомоморфизм из путей плюс-минус 1, который я выберу правильно, так, чтобы у меня каждый раз получалось единица.
Надо подумать, я сходу не скажу. Окей. This is very useful formula, but also there is another useful formula. We may consider a slightly more general situation. We may be interested not only in intersection index of f of b with b, but of intersection index of f of b with any c. Then the situation is more difficult, and we have no good.
In terms of inner intersection?
Yeah, in terms of some intersection index. We have no complete answer, but we have a very nice estimate. So if we are interested in such number, first of all, how does it look like? What is our hope? What do we want to have? Look again on this beta prime. Assume that we had another curve gamma. Which was in minimal position to both beta and alpha. We can do it, okay? This gamma is in this isotopy class C. Okay, we have, and so we have I of B. Of course, we can achieve that all intersections with beta are outside these strips, are far from these strips. And also all intersections with alphas are far from intersections with betas. Yes? So, how we have so many intersections with beta, and these intersections they are still intersections with beta prime. We have the same number of intersections with beta primes, but now every such arc from here to here, yes, every such arc intersects gamma, but how many times? K times A of AC. It intersects this arc, intersects gamma. Gamma intersects with alpha several times, and we go through every such intersection k times. So, and now again we need to multiply it by E of AB. Yes. So the some maximal number of intersections which may achieve. What we know? We know that this one is smaller or equal than the sum of G. Again, all K's are of the same. But this estimate is true. Yeah, here we do not need that they are of the same kind. We need to take this one times this one. Again, if we have several alphas, then we just take the sum plus the number of intersections from the very beginning. Okay. And now claim a very useful claim is that if all kj's are of the same signs, if all kj's have the same sign, then in fact the following estimate is true. The difference between this and this is not okay. I just write down the answer. This is less than or equal than the intersection number of B and C. One of these, okay, we have here the absolute value. One of these is exactly this. We see that this one is less than or equal than that plus I of BC. So we need to prove the lower bound. This one is what we already know, but now we need to prove that this guy is greater than or equal to the sum minus I of BC. Well, let us try to think how to prove things like that.
Это очень странно, потому что вот это слагаемое, оно там точно должно быть.
У тебя эти пересечения могли двухугольники образовываться.
The idea is that bigons may appear only because of these intersection numbers, or only because of these points. And deleting every such beigen, we delete one point from here and one another point. So we maximally can delete as many points out of this number. But this is some idea, this is not, not a proof. А во сколько должен закончить? 14:20. Все.
Если проверить то, что можно подкручивать ориентацию, тогда это более-менее очевидно, потому что время...
Сейчас, давайте попробуем это. Я что-то не понял все-таки аргумента.
Можно действительно привыкнуть, что один индекс не просто, а умножая на некоторые гоморфизмы с P1 в Z. Вот. Потому что для кривые они будут петлю, вот, и можно подкрутить на это. Ну, на гоморфизм.
А чем вам, Саша, например, не понравился, пардон? Ну, то есть,
не, это не аргумент. То, что я сказал, это вот доказательство бесконечно.
Ну, мы же как бы вот из того, что мы уже обсуждали, вроде понятно, что вот эти, ну вот на местах пересечения с А, там вот внутри прямоугольников, по идее, не могут. Сейчас давайте считать, что n равно единичке для простоты сейчас. Ну, вроде мы обсудили, что на местах пересечений с А двуугольников появиться не может.
Мы эти убавим двуугольники, а потом надо понять, что их оставшиеся в остальном ничего нет.
Не понял. Зайн, ты вот...
Какие мы эти убрали? Я так помахал руками, что здесь что-то может возникнуть.
А что получилось, не знаю.
Ну там останется внутри прямоугольничков что-то там туда-сюда.
Да, можно, да, взять и если у нас... правда ли, что все эти петли, они независимы, если мы можем задать какой-нибудь морфизм из P1, чтобы знаки были какие-нибудь.
Не, здесь петли сильно зависимы могут быть. А, вот, я понял, чего хотите. Не знаю, это не так просто все. Гомоморфизм. Нет, может быть, идея хорошая, но это надо с этим хорошо продумывать.
Там как раз противоречит гомоморфизму как раз то, чтобы у нас какой-то образовался байгон, в котором у нас, с одной стороны, мы хотим пар, чтобы плюс, и с другой стороны, минус.
Ну да, да.
А таких не будет, потому что у нас в минимальном положении кто-то там, где не хотят байгона. Ну, кажется, что то есть так.
Ну, да, мы скажем точку пересечения сейчас со знаком, который образ гомоморфизма, но петли, понятно.
Ну, это надо гомоморфизм. Я пока не понимаю, как гомоморфизм строить.
Ну, мы хотим вот так и построить, а потом сказать, что он есть, потому что противоречие к нему было бы существование байгона, в котором у нас было бы как раз это противоречие, собственно, ну, скорее всего. Ну, там чуть-чуть, да. Ну, было бы очень хорошо.
Было бы хорошо, да. Well, actually, here there is some trick, and maybe it is better that I tell you which trick is here. Let us. No. Let us put this gamma in minimal position with both beta and beta prime. Just in minimal position with beta prime, it is enough. So we may put gamma. Before it was with beta prime and alpha. This is what I want. And again, we may assume that all intersection points are far from these intersection points, far from here. Is it true? Sorry. No, it is not. Well, and why can we do this? Why can we do this? Well, no.
Вопрос в смысле, почему мы можем увести точки пересечения?
Нет, смотрите, если мы не заботимся о пересечениях с бета, да, то почему наша гамма не начнет ходить вот здесь вот? Да, она может как-то вот так вдоль идти, да, между точками пересечения. Сейчас. Я хочу сказать, что я могу ее одновременно привести в минимальное положение с бета и бета-штрихом, но вот это чуть хитрее, потому что это не совсем то, что мы доказывали. Мы доказывали для неизотопных кривых.
Бета и бета-штрих.
Они не в минимальном положении. Бета и бета-штрих друг с другом точно не в минимальном положении, они кучу раз пересекаются.
Здесь уже было минимальное положение, это когда...
Сейчас, бета-штрих, что такое бета-штрих?
Бета-штрих это вот эта штука, которую мы построили, которая ходит.
Это F.
Так она...
Нет, она вместе с бета она точно не в минимальном положении. Подождите.
Сейчас, что значит минимально? Мне казалось, что они...
Sorry. We have proved that beta and beta prime are in minimal position. Что-то на меня помрачение нашло. Beta is the original curve. Beta prime is the curve in this f of b, which we have constructed. And we have proved that they are in minimal position. This is exactly this equality.
Бета это то же самое, что Б?
Да, beta is a curve in isotopy class B. So, beta and beta prime are in minimal position. Yes? Now let us put gamma in minimal position to both of them. We may do this. So we may put gamma in minimal position with both of them simultaneously. We may do this by lemma, which we have proved. Okay.
Со всеми тремя нельзя?
Со всеми тремя, может и можно, по-моему, просто не нужно. Let us look here. I would like to make some opposite surgery. I would like vice versa to transform this beta prime to beta. I would like to do the following. Look at every crossing. Here is beta, here is beta prime, and now I consider this strip, and here I have plenty of and the last one goes here. Yes? I would like to do the following. I take this one and here this one will go in such way. This one will go in such way. I modify my curves. So when I arrive here, I make one step right. And the same in all intersections. And this one will go straight. So I have modified my curves. In this region, I have modified my curves. This one went here, but instead, now it goes such way. Мы всегда делаем один шаг вправо. Вместо того, чтобы первая была соединена с этой, вторая была соединена с первой, третья была соединена со второй, четвертая с третьей и так далее. А мы их переразбили по-другому.
Так, чтобы было много. Чтобы они перестали быть связаны.
Да. Now, if we make this, now again, in every such section, we have many curves. How many curves? We have, if this is alpha g, we have kj times I of ajb. Yes? This is the number of arcs, of these green arcs. But now we make them, if we make the same procedure in all если мы то же самое сделаем во всех точках пересечения, мы получим просто прямые вдоль полосы, да? We will get as many curves, each of which is in alpha g, in homotopy class alpha ag. Ну просто первая все время идет первой, и она так и замкнется первой. Вторая, вот это не получается. After this procedure, the number of crossings on these, I consider only, actually this curve is not interesting to me. I consider only the number of crossings on these green curves. The number of crossings of green curves, cap, the number of crossings with gamma. With gamma, we can compute them, or at least we can estimate them. We have at least any curve in AG has at least I of AGC crossings with gamma. So this we have as many curves. So we have estimated that this is we have such estimate. So we, instead of considering our curve beta prime, we consider new set of curves, these green curves. Yes? And we say that, okay, their number of crossings with gamma, we do not know whether they are in minimal position or not, but at least we can always estimate that it is not smaller than this one. At least this number, since if they were in minimal position, then it would be exactly this number. But now, let us look on our green curves. These green curves together constitute part of beta prime. This is not the whole beta prime. Beta prime always have these arcs between strips, but part of beta prime, and also these part of beta. So this is less than or equal than the number of crossings of beta with gamma. plus the number of crossings of beta prime with gamma. We have part of beta and part of beta prime. Okay. And this is what is required. So this is exactly, since they are in minimal position, this is exactly I of BC plus I of F of BC. This is exactly what we need. So, okay. So, this is a nice estimate. Just to at next lecture we will obtain more consequences of these two facts. But now let us start with an easy one, but still important. So assume that we have two different essential curves. Different, I mean up to non-isotopic. And we consider den twists about them. If the first question is it possible that these den twists are equal to each other? Maybe we take two different curves, but the resultant mapping class is the same. At least it is not obvious. It is not obvious. Why not? When we consider mapping classes, when we consider homeomorphism up to isotopy, then we do not require that through this isotopy homeomorphism is a den twist. We just consider any isotopy, yes? And it may happen that, okay, we make some difficult isotopy and one mapping class transforms to another. But in fact, this is impossible. So a useful claim is that if A and B are isotopy classes of essential simple closed curves, and A is not equal to B, so the curves are not isotopic to each other, then the den twists are not equal to each other. Why? Let us prove this. Actually, we have two possibilities. First one, let us suppose that the intersection index of A and B is non-zero. Then we may apply just the den twist TA to B and take the intersection index with B. And our formula says us that we get, in this case, we just get EA of B squared, and this is not zero. But if we take the intersection index of TB of B, TB of B is just B itself, since the den twist never changes this particular curve. But the intersection index of a curve with itself is always zero. Okay, so TA is not equal to TB. Yes? But, okay, we have second situation that maybe E of AB equal to zero. How to proceed in this situation?
Нужно найти какой-то третий прибор.
Yes. Actually, how does this let us look, how does this situation looks like? Actually, we have already discussed that there is a very useful thing called change of coordinates principle. That if we have a simple closed curve, then all simple closed curves that are not separated look in the same way. We can up to homeomorphism, they are all identical. They can be taken to each other. In the same way, if we have pairs of disjoint curves, then again we have only finitely many possibilities up to homeomorphisms. And these possibilities are the only thing is that when we cut surface, we can get several. There are several possibilities for the number of pieces, several possibilities for their genera. So what is possible? It is which situations are possible? There is a situation when these alpha and beta, they are just disjoint. So there is a situation when they together not separate the surface. And then, well, they up to homeomorphism, they always look like here. We may consider only this. Also, it is possible that they are either of them is non-separated, but together they separate the surface. Okay, there are several possibilities depending on genera here, but again, it looks like that. What is also possible? It is also possible that one of them is separated and another is not non-separated. Well, since alpha and beta, it is not important for me which one is alpha and which one is beta, then, okay, we can rename them if needed. And the last possibility is that both are separated. So again, we have several possibilities for genera here. Look, in any case, we can point out a curve, a new curve, such that it has non-zero intersection index with alpha, but zero intersection index with beta. Just we have for cases, okay, it is easy to find. Here it is like that. Here it is like in the same way. Here it is more interesting. It is not possible to achieve that the intersection index with alpha is 1, since the algebraic intersection index with alpha and beta are the same, but it is possible to achieve the intersection index 2. There is such separating curve. It is easy to see that it is in minimal position with alpha, since there are no bigons. No bigons, since both these parts are of positive genus. If one of them was of zero genus, then alpha and beta were isotopic. So here and here, say this one. Yes. Again, index 2. So now we may denote the isotopy class of gamma by C. We may compute. With C. Yes. First, it is equal to this squared, yes? And hence it's not 0. But if we take TB of C, then, okay, since B is just disjoint from C, we even don't need that formula. It is just C with itself, and it is 0. And again, we come to a contradiction. We see that TA is not equal to TB. There is a very nice consequence. This may seem to be more or less expect. So we expect something like that. Maybe first thing which I would like to say, we have, when we discussed Fenchel-Nielsen coordinates, we have obtained a corollary that if we have a multi-curve, pairwise non-intersection, pairwise non-isotopic curves, then the den twists generate a free abelian group. A good exercise is that the same can be proved without any Fenchel-Nielsen coordinates, without any hyperbolic geometry. Just if alpha 1, alpha n are essential simple closed curves that are pairwise non-isotopic and pairwise disjoint. Then the den twists generate a free abelian group of rank n, generate a free abelian subgroup of the mapping class group. A good exercise is to prove this using such estimates, using their that all their combinations act differently on curves, and this is enough. And another easy but important consequence is the following corollary, and I just formulated, and we will stop, more or less. Corollary: assume that there is a mapping class group which commutes, a mapping class which commutes with a den twist. So we have an arbitrary element of mapping class, and just assume that it commutes with some den twist. Then F takes this isotopic class of curves to itself. So hence F can be represented by a homeomorphism which stabilizes the curve, a curve in. Proof. What is always true? It is always true that T of F of A equals F TA F minus. Just F minus F inverse takes F of A to A, we perform den twist and then map it back. So this is always true. And if this is always true, always. If we have this one, then we see that T of F of A equals TA. Hence, we see that these two isotopic classes. So it is very convenient that if just we have some identity in mapping class group, if we have an element which commutes with a den twist, then automatically we see that this element can be represented by a homeomorphism that stabilizes the corresponding curve. Well, I think it's time to finish for today. Sorry for delay. That's all.